Hello there, and welcome. Tonight I want to take you somewhere far beyond the familiar comforts of our small blue world, somewhere that exists at the very edge of human understanding, where light itself behaves in ways that have puzzled the greatest minds of our time. I want you to settle in now, wherever you are, perhaps beneath soft blankets, perhaps with your eyes already growing heavy, and let me guide you through one of the most extraordinary mysteries the universe has ever whispered to us. This is a journey we will take together, you and I, moving slowly through the darkness between stars, drifting past galaxies that spin like quiet pinwheels in the cosmic night, until we arrive at a place where light becomes something almost unimaginable, something so powerful and yet so fleeting that for decades scientists could barely believe what they were seeing. Before we begin this voyage into the deep unknown, I want to ask you something. If you find yourself moved by what we discover tonight, if this journey through the cosmos brings you a sense of wonder or peace, perhaps you might consider subscribing to join us on future expeditions into the mysteries of space. And I am curious, as we gather here together from all corners of the Earth, where are you watching from right now? What time is it where you are? Perhaps it is late evening and the stars are just beginning to emerge outside your window. Perhaps it is the deep hours of the night when the world has grown still and quiet. Wherever you are, whatever hour holds you in its gentle embrace, know that you are welcome here, and that together we're about to explore something truly remarkable. Now, let us begin with something simple, something so fundamental to our existence that we rarely pause to consider its profound strangeness. Let us begin with light itself. You see, at this very moment, as you listen to these words, light is doing something extraordinary. It is traveling. It is always traveling. From the lamp beside your bed, from the screen before your eyes, from the distant stars that pepper the night sky, light is moving, perpetually moving, at a speed so constant and so absolute that it forms the very backbone of how we understand reality. 300,000 kilometers every single second. That is how fast light travels through the vacuum of space. It is a speed so immense that our minds struggle to truly grasp it, and yet it is also a speed that never changes, never varies, whether the light comes from a candle flame or from the heart of an exploding star. Consider for a moment what this means. When you look up at the night sky, you're not seeing the universe as it is right now. You're seeing the universe as it was, because the light reaching your eyes has been traveling, sometimes for unimaginable lengths of time before finally arriving at this precise moment to meet your gaze. The light from our moon takes just over a second to reach us. The light from our sun takes about 8 minutes. But the light from other stars, from other galaxies, from the most distant reaches of the observable universe, that light has been traveling for millions, even billions of years. When you look at a distant galaxy, you're looking back in time, seeing that galaxy not as it exists today, but as it existed when that light first began its journey, perhaps before our own planet had even formed. This is the nature of light, this beautiful, patient messenger that carries information across the cosmos. And yet, here is where our story takes its first intriguing turn. You see, not all light is the same. The light we see with our eyes, the light that illuminates our days and reveals the colors of the world around us, this visible light is only a tiny fraction of a much larger spectrum. There are forms of light that we cannot see, forms of light that exist beyond the range of human perception, and these invisible lights carry their own secrets, their own stories, their own profound mysteries. Perhaps you've heard of radio waves, those long, gentle undulations of electromagnetic energy that carry music to your car radio and voices to your phone. Perhaps you've heard of infrared light, the warmth you feel radiating from a fire invisible to your eyes but sensed by your skin. Perhaps you have heard of ultraviolet light, the rays from our sun that can burn unprotected skin, or X-rays, those penetrating beams that allow doctors to peer inside our bodies. All of these are forms of light, different expressions of the same fundamental phenomenon, differing only in their energy and their wavelength. Radio waves are long and lazy, stretching out over meters or even kilometers. Visible light is shorter, its waves measured in tiny fractions of a millimeter. And as we move through the spectrum, here, the waves grow shorter still and the energy grows higher, until we reach a realm of light so energetic, so powerful, that it defies easy comprehension. This realm is the domain of gamma rays, and it is here, in this most extreme territory of the electromagnetic spectrum, that our story truly begins. Gamma rays are light, yes, but they are light of a kind that seems almost alien to our everyday experience. Their wavelengths are measured in picometers, trillions of times shorter than the waves of visible light. Their energy is so immense that a single gamma-ray photon carries more power than millions of visible light photons combined. They are born in the most violent and extreme environments the universe can create, forged in conditions of heat and pressure and magnetic fury that exist nowhere on Earth. And they travel across the cosmos carrying with them information about events so cataclysmic that they beggar the imagination. And yet, despite their power, gamma rays from space cannot reach us here on the surface of our planet. Our atmosphere, that thin blue shell of air that wraps around the Earth like a protective blanket, absorbs gamma rays before they can reach the ground. For most of human history, we had no idea that gamma rays from space even existed. We could not see them, could not detect them, could not imagine that somewhere out there in the cosmic darkness, light of such extraordinary intensity was being produced in quantities that would one day reshape our understanding of the universe. It is a humbling thought, is it not? To consider how much of reality exists beyond the reach of our natural senses, how much of the universe's story is being told in languages we were never equipped to hear. And yet, this is also what makes the human spirit so remarkable. We found ways to listen. We built instruments that could detect what our eyes could not see. We launched satellites above our atmosphere's protective embrace and turned our technological ears toward the sky, hoping to catch whispers of these invisible lights. And what we found, what we discovered waiting for us in the darkness between stars, was something that no one had predicted, something that would become one of the greatest mysteries in the history of astronomy. We found gamma-ray bursts, brief, intense flashes of gamma-ray light appearing suddenly in the sky, blazing with inconceivable brightness for just a few seconds or minutes, and then vanishing, leaving behind only questions and wonder. These bursts were not coming from our sun, not coming from nearby stars, not coming from anywhere within our own galaxy. They were coming from the deepest reaches of space, from distances so vast that the light had been traveling for billions of years before reaching our detectors. And in those brief moments of brilliance, these gamma-ray bursts were outshining everything else in the observable universe, releasing more energy in a few seconds than our sun will produce in its entire 10 billion-year lifetime. It is a question that might seem almost absurd at first. This notion that there could be events so powerful, so luminous, so utterly extreme. It's a question that many scientists initially doubted, but one that built gentle intrigue as the evidence accumulated. What if the universe contained phenomena so far beyond our everyday experience that they seemed almost impossible? What if, hidden in the darkness between galaxies, there were cosmic lighthouses flashing with a brilliance that defied comprehension? What if these gamma-ray bursts were trying to tell us something about the nature of reality itself, about the extreme conditions that exist at the boundaries of what is possible? Let us settle deeper into this mystery together, you and I. Let us slow our breathing and open our minds to the vast strangeness of the cosmos. The universe is not required to make sense to us. It is not obligated to fit neatly into the categories of our understanding. And perhaps that is what makes it so beautiful, so worthy of our wonder and contemplation. The universe surprises us. It humbles us. It shows us again and again that there is always more to discover, always another layer of mystery waiting to be explored. Think about light once more, about this remarkable phenomenon that connects us to the distant cosmos. Light is patient. Light is persistent. A photon of light once created will travel forever unless something absorbs it. It does not grow tired. It does not slow down. It simply moves at that constant, unwavering speed through whatever emptiness lies before it. And as it travels, it carries information, encoded in its wavelength and its energy, about the conditions of its birth. When we detect light from a distant star, we are learning about that star, about its temperature and composition, about the processes occurring within it. When we detect light from a distant galaxy, we are learning about that galaxy, about its structure and motion, about its place in the cosmic web. And when we detect gamma rays from a gamma-ray burst, we are learning about something truly extraordinary. We are catching a glimpse of the most energetic processes the universe has ever created, processes that push the laws of physics to their absolute limits. These are not gentle phenomena. These are not quiet, peaceful emissions of energy. And yet, as we explore them tonight, we will find that there is a kind of peace in understanding them, a kind of comfort in knowing that even the most extreme events in the cosmos follow patterns and rules that our patient investigation can slowly reveal. Perhaps you're beginning to feel the weight of sleep settling upon you now, that gentle heaviness in your limbs, that softening of the world around you. That is good. That is welcome. This journey we're taking does not require alertness or tension. It asks only for your presence, your willingness to drift along these currents of thought, to let the words wash over you like starlight falling softly on a quiet sea. The cosmos is vast and we are small, but in this smallness there is intimacy. In this smallness there is connection. We are made of the same atoms that burn in distant stars. We are, in a very real sense, the universe contemplating itself, wondering about its own nature, marveling at its own mysteries. And so we arrive at the threshold of our exploration, standing at the edge of understanding, peering into the darkness where gamma-ray bursts flicker and fade. These enigmatic flashes of light have puzzled scientists for over half a century. They have inspired theories and debates, observations and discoveries, and slowly, patiently, persistently, we have begun to unravel their secrets. We are beginning to understand why gamma-ray bursts produce light of such extraordinary energy, why they are, in a sense, the fastest light in the universe, not faster in terms of speed, for all light travels at the same cosmic velocity, but faster in terms of frequency, faster in terms of the energy each photon carries, faster in the sense that they represent light at its most extreme and powerful. This is the story we will explore together as the night deepens around us. We will travel back to the accidental discovery of these cosmic phenomena, to the Cold War satellites that stumbled upon a mystery they were never designed to find. We will journey through the electromagnetic spectrum, coming to understand what makes gamma rays so special, so different from the visible light our eyes were built to see. We will witness the birth and death of massive stars, the collision of impossible objects, the creation of light so intense that it outshines entire galaxies. And through it all we will maintain our sense of wonder, our appreciation for the beautiful strangeness of the universe we inhabit. For now, let us simply rest in this moment of introduction, in this threshold space between the known and the unknown. Let the questions settle gently in your mind like snow falling on a still landscape. What are gamma-ray bursts? Where do they come from? Why do they produce such energetic light? These questions will guide us through the hours ahead, but there is no urgency in answering them. The universe has been keeping these secrets for billions of years. It will not mind if we take our time in understanding them. Perhaps as you listen, you are watching the play of shadows on your ceiling, or the soft glow of distant streetlights through your window. Or perhaps your eyes have already closed, and you're simply drifting on the sound of these words. Whatever your state, you are exactly where you need to be. This is a journey that welcomes all travelers, whether wide awake or hovering at the edge of dreams. The cosmos does not discriminate. It shines its light upon us all, waiting patiently for us to look up and wonder. And wonder is what we shall do. Together, gently, peacefully, we will explore one of the great mysteries of modern astronomy. We will discover why gamma-ray bursts have captivated scientists for decades, why they represent something truly unique in the cosmic landscape, and why, after all these years of observation and study, we are finally beginning to understand the mechanisms that make them possible. It is a story of human curiosity and technological ingenuity, of patient observation and brilliant insight, and above all, it is a story of the universe itself, revealing its secrets to those who take the time to listen. So settle in, dear traveller. Let the weight of the day slip away from you. Let the concerns of tomorrow fade into the background. For the next few hours there is only this: the gentle exploration of light at its most extreme, the peaceful contemplation of cosmic mysteries, and the quiet companionship of a journey shared. The universe is vast and strange and beautiful, and tonight we will touch just one small corner of its infinite wonder. Light, as we have begun to explore, is something more complex and varied than our everyday experience might suggest. The light that fills our world, that illuminates our days and reveals the faces of those we love, represents only the narrowest slice of a much broader phenomenon. If we could see the full electromagnetic spectrum, If our eyes were sensitive to all the wavelengths of light that permeate the universe, the world around us would appear utterly transformed. We would see radio waves emanating from our electronic devices, curling and rippling through the air like invisible smoke. We would see the infrared glow of warm bodies, the soft heat signature of living things and running engines. We would see the ultraviolet haze of the sun, the X-ray flicker of distant cosmic sources, and beyond all of these we would see the gamma rays, those most energetic messengers, streaming in from the depths of space. But our eyes evolved for a different purpose. They evolved to help us navigate the world immediately around us, to find food and avoid predators, to recognize friends and read the expressions on human faces. For these tasks, visible light serves admirably. It tells us what we need to know about our immediate environment with remarkable precision and beauty. But it tells us almost nothing about the universe beyond our small blue planet. Almost nothing about the extreme conditions that exist in the hearts of stars and the spaces between galaxies. Almost nothing about the extraordinary range of phenomena that make up the cosmic story. This is why we build instruments. This is why we launch satellites into orbit and position telescopes on mountaintops and construct vast arrays of radio dishes across desert plains. We are extending our senses, reaching out with technological prostheses to detect what our biological equipment cannot perceive. And in doing so, we have discovered a universe far stranger and more wonderful than our ancestors could have imagined. The discovery of gamma rays themselves came in the late 19th century, when scientists studying radioactive materials noticed that certain atoms emitted not just particles, but also a form of radiation that could penetrate materials that stopped even X-rays. This radiation was given the name gamma rays, the third letter of the Greek alphabet, following alpha and beta radiation, which had been discovered earlier. At that time, no one imagined that gamma rays might come from space. The very idea would have seemed fanciful, for what cosmic process could produce such energetic light? But the universe, as we have noted, is not constrained by our expectations. It contains phenomena far beyond the scope of early 20th century imagination, and among these phenomena, gamma-ray bursts would prove to be among the most spectacular and mysterious. Their discovery, however, would not come from astronomers peering through telescopes at the night sky. It would come from a most unexpected source: satellites designed to detect nuclear weapons tests. Let us travel back now, in our minds, to a time of tension and fear, a time when the great powers of the Earth stood poised at the brink of mutual annihilation. The Cold War cast a long shadow over the middle decades of the 20th century, and among its many consequences was an intense competition in nuclear weapons development. The United States and the Soviet Union built arsenals of unprecedented destructive power, and with this power came suspicion and the need for verification. How could one nation know if another was testing nuclear weapons in secret, violating treaties and pushing the arms race toward ever more dangerous territory? One answer came from space. In 1963, the United States signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, in outer space and underwater. To verify compliance with this treaty, the United States launched a series of satellites known as the Vela satellites. These spacecraft were designed to detect the gamma rays produced by nuclear explosions. Every nuclear detonation releases a distinctive signature of gamma ray radiation, and by monitoring for this signature from orbit, the Vela satellites could detect treaty violations anywhere on Earth or in the near-space environment. The Vela satellites were quiet sentinels, orbiting the Earth in patient vigil, their instruments tuned to the telltale flicker of nuclear fire, and for years they performed their function admirably, watching, waiting, ready to sound the alarm if any nation broke its word. But in July of 1967, something unexpected happened. The satellites detected a burst of gamma rays unlike anything they were designed to find. This burst did not match the signature of a nuclear explosion. It was too short, too intense, too strange. The scientists who analyzed the data were puzzled. They checked their instruments, wondering if there had been some malfunction, some spurious signal that had triggered a false alarm. But the data was solid. The gamma rays were real, and they had not come from Earth. Imagine the moment of realization, the slow dawning of awareness that something truly extraordinary had occurred. These scientists were not astronomers. They were military researchers focused on the very terrestrial concerns of nuclear proliferation. But suddenly, unexpectedly, they found themselves holding evidence of a cosmic phenomenon that no one had predicted, no one had theorized, no one had even imagined. The detection was kept classified for years as the military tried to understand what it meant and whether it had any implications for national security. But eventually, in 1973, the discovery was published in a scientific journal, and the astronomical community was introduced to one of the great mysteries that would occupy their attention for decades to come. Gamma-ray bursts, as they came to be called, had arrived on the scientific stage, and nothing would ever quite be the same. Perhaps there is something poetic in this origin story, something that speaks to the unexpected ways that knowledge advances. Here was a technology built for war, designed to detect the most destructive weapons humanity had ever created, and yet it became the instrument through which we discovered one of the most magnificent phenomena in the natural world. The same gamma rays that marked nuclear explosions also marked events of cosmic significance, events occurring not in secret military tests but in distant galaxies, billions of light years from Earth. It is as if the universe had been waiting for us to develop the tools to see it, patiently sending its signals across the cosmos, confident that eventually we would find a way to listen. If you are still with me now, still drifting on these words as they carry you through the darkness, I would love to know what you think of this strange origin story. Consider leaving a comment below, sharing where you're watching from and what time of night holds you in its embrace. These journeys through the cosmos are always richer when shared, when we know that others are traveling alongside us, contemplating the same mysteries, wondering at the same strange and beautiful universe. The discovery of gamma-ray bursts posed immediate and profound questions. Where were these bursts coming from? What could possibly produce such intense flashes of gamma-ray light? And why were they appearing seemingly at random, from all directions in the sky, with no apparent pattern or source? The Vela satellites continued to detect them, sometimes several times a year, each burst as mysterious as the last. Scientists proposed theories, debated possibilities, and launched new missions to gather more data. One of the first questions was distance. Were gamma-ray bursts nearby, perhaps originating in our own solar system, or in the halo of stars surrounding our Milky Way galaxy? Or were they far away, coming from distant galaxies, or even from the edges of the observable universe? The answer to this question would have profound implications for understanding the energy involved. If the bursts were nearby, they might be relatively modest events, appearing bright only because of their proximity. But if they were far away, if the light had traveled for millions or billions of years before reaching us, then the energy involved would be almost inconceivable. For many years, this question remained unresolved. The Vela satellites and their successors could detect gamma-ray bursts, but they could not pinpoint their locations with sufficient accuracy to identify the source. It was like hearing thunder but not being able to see the lightning, knowing that something powerful had happened but not knowing where. The bursts appeared uniformly distributed across the sky, giving no clear clue about their origin. They did not cluster along the plane of our galaxy as they might if they came from nearby stars. They did not show any preference for particular directions or regions of space. They simply appeared, flared briefly, and vanished, leaving behind only data and questions. The breakthrough came in the 1990s with the launch of the Compton Gamma Ray Observatory, a NASA satellite dedicated to studying gamma-ray astronomy. One of its instruments, the Burst and Transient Source experiment, was designed specifically to detect and locate gamma-ray bursts, and while its positioning was still not precise enough to identify optical counterparts, it accumulated a vast catalogue of bursts that confirmed their uniform distribution across the sky. This uniformity suggested that gamma-ray bursts were not local phenomena, but rather events occurring at cosmological distances, coming from galaxies scattered throughout the observable universe. But the definitive proof came in 1997, when another satellite, the Italian-Dutch BeppoSAX, detected a gamma-ray burst and quickly relayed its position to ground-based telescopes. For the first time, astronomers were able to point their optical instruments at a gamma-ray burst while it was still fading, and what they saw confirmed the cosmological hypothesis beyond any doubt. The burst had occurred in a distant galaxy, billions of light years from Earth. The light had been traveling for most of the age of the universe before reaching our instruments, and this meant that the energy involved was staggering, almost beyond comprehension. Think about what this means for a moment. A gamma-ray burst lasting perhaps a few seconds was releasing more energy than our Sun will produce in its entire 10 billion year lifetime. It was outshining all the stars in its host galaxy combined. It was, for that brief moment, the brightest object in the observable universe. And it was doing all of this through the emission of gamma rays, the most energetic form of light known to physics. How is such a thing possible? What process could concentrate so much energy into such a brief burst of such high-frequency light? These questions drove a generation of research, inspiring new theories, new observations, and new missions designed to catch gamma-ray bursts in the act and study them in unprecedented detail. And slowly, patiently, persistently, the answers began to emerge. But that story, the story of how we came to understand the mechanisms behind gamma-ray bursts, is a journey that lies ahead of us. For now, let us rest in this moment of historical context, appreciating the path that brought us here. From Cold War satellites to orbiting observatories, from unexpected discoveries to confirmed cosmological distances, the story of gamma-ray bursts is a testament to human curiosity and ingenuity. It reminds us that the universe always has more to teach us, that there are always phenomena waiting to be discovered, mysteries waiting to be explored. And as you drift deeper into the night, as the world around you grows quieter and more still, perhaps you can take some comfort in this thought. We are a species that looks up. We are a species that asks questions, that builds instruments to extend our senses, that reaches out into the unknown with curiosity rather than fear. Whatever mysteries the universe holds, we face them together, one discovery at a time, one question at a time, one peaceful night of contemplation at a time. The gamma rays that stream in from distant galaxies have been traveling for billions of years. They carry information about events that occurred when our planet was young, when life on Earth was just beginning its long evolutionary journey, when the universe itself was a different place than it is today. And now, finally, they have arrived here, at this moment, to meet our instruments and our wandering minds. There is something beautiful in that connection, something that links us across unimaginable distances and spans of time to the cosmic processes that shape the universe we inhabit. So let us continue our journey together, you and I, drifting through the darkness, following the light. There is so much more to discover, so much more to wonder about. The night is long and the cosmos is patient, and somewhere out there in the infinite darkness, gamma-ray bursts are still flashing, still calling to us across the void, waiting for us to understand their secrets. The electromagnetic spectrum, that vast range of light that permeates our universe, is something worth contemplating more deeply as we continue our journey into the night. Imagine it as a great cosmic piano, stretching from the deepest bass notes to the highest treble, from rumbling radio waves to screaming gamma rays. Every key on this piano represents a different wavelength of light, a different frequency, a different energy level. And when the universe plays this piano, it plays all the keys at once, filling the cosmos with an endless symphony of electromagnetic radiation. At the lowest end of the spectrum, we find radio waves. These are the gentle giants of the light family with wavelengths that can stretch from a few millimeters to several kilometers. They are the waves that carry radio broadcasts, television signals, and wireless internet data. They are also produced naturally by many cosmic objects, from the swirling gases of nebulae to the spinning cores of pulsars. Radio waves have relatively low energy, which is why they pass harmlessly through our bodies, why we can bathe in them constantly without any ill effect. They are the whispers of the electromagnetic spectrum, soft and pervasive and everywhere. Moving up in frequency, we encounter microwaves, those versatile waves that heat our food and carry our cell phone conversations. Beyond microwaves lies infrared light, the heat radiation that all warm objects emit, the invisible glow that night vision cameras are designed to detect. Infrared light shows us a world of temperature, a world where warm bodies stand out against cool backgrounds, where the living and the active shine brighter than the still and the cold. And then, in a narrow band that seems almost unreasonably small given its importance to us, we find visible light. Red, orange, yellow, green, blue, indigo, violet. The colours of the rainbow, the colours of our world. These wavelengths, ranging from about 700 nanometers for red light to about 400 nanometers for violet, are the only ones that our eyes can detect. They represent a tiny fraction of the electromagnetic spectrum, a mere sliver of the cosmic piano, and yet they define our visual experience of reality. Everything we see, every color and shade and pattern, is encoded in this narrow range of frequencies. Beyond visible light, the frequencies continue to climb. Ultraviolet light, invisible to us but visible to bees and other creatures, carries enough energy to damage living tissue, to cause sunburns and cataracts. X-rays, more energetic still, can penetrate soft tissue and reveal the dense structures of bones and teeth. They're used in medicine and security, but they must be used carefully, for their energy can damage living cells. And at the very highest end of the spectrum beyond X-rays, we find gamma rays. These are the sopranos of the cosmic piano, the highest notes, the most energetic photons. Their wavelengths are measured in picometers, trillions of times smaller than the wavelengths of visible light. A single gamma ray photon can carry millions of times more energy than a photon of visible light. They are born in the most extreme environments the universe can create, in nuclear reactions, in particle accelerators, in the hearts of exploding stars, in the violent collisions of cosmic objects. Here is something important to understand, something that sits at the heart of our exploration tonight. All light travels at the same speed. Radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, they all move through the vacuum of space at exactly the same velocity, approximately 299,192 kilometers per second, the universal speed limit, the cosmic constant that Einstein recognized as fundamental to the nature of reality. No form of light is faster than any other form of light in terms of this velocity. They all race through the cosmos at the same breathtaking pace. And yet, when we say that gamma ray bursts produce the fastest light in the universe, we are speaking of something else, something more subtle and perhaps more profound. We are speaking of frequency, of energy, of the rate at which the electromagnetic waves oscillate as they travel. A radio wave might complete a few million oscillations per second. A wave of visible light oscillates hundreds of trillions of times per second. But a gamma ray oscillates at frequencies beyond 10 to the 20th power cycles per second, a number so vast that it loses meaning in everyday terms. This frequency is directly related to energy. The higher the frequency, the higher the energy each photon carries. This is the insight that quantum physics provided in the early 20th century, the realization that light comes in discrete packets called photons, and that the energy of each photon is determined by its frequency. A gamma ray photon with its incredibly high frequency carries an enormous amount of energy compared to its lower frequency cousins. It is light at its most potent, light at its most extreme. And gamma ray bursts, those mysterious flashes from the depths of space, produce gamma rays in quantities and intensities that boggle the mind. For a few brief seconds, a single gamma ray burst can release more gamma ray photons than our sun will produce in its entire existence. The energy output is so extreme that it challenges our ability to comprehend it, forcing us to reach for analogies and comparisons that always fall short of capturing the true magnitude. Consider this. If you could somehow convert all the mass of our sun into pure energy, following Einstein's famous equation E equals mc squared, you would get a number almost inconceivably large. The sun contains roughly 2 times 10 to the 30th power kilograms of matter, and converting that to energy would yield approximately 1.8 times 10 to the 47th joules. This is more energy than humanity has used in all of history, more energy than we could use in millions of years of current consumption. And yet, a single gamma ray burst can release energy approaching this value in just a few seconds. Some of the most powerful bursts ever observed have released estimated energies of 10 to the 44th to 10 to the 47th joules, an almost incomprehensible output that rivals the complete matter-energy conversion of a stellar mass. How does the universe create such events? What cosmic processes can concentrate so much energy into such brief, intense bursts of the most energetic light possible? These questions haunted astronomers for decades after the initial discovery of gamma ray bursts. The answers, when they finally began to emerge, would reveal mechanisms of extraordinary violence and complexity, processes involving the death of massive stars, the collision of exotic objects, and the warping of space and time itself. But even as we contemplate these violent origins, there is a strange peace to be found in the contemplation. For we are far from these events, separated by billions of light years and billions of years. The gamma-ray bursts we detect are ancient history, events that occurred in the distant past of a younger universe. By the time their light reaches us, they are just data, just patterns of detection in our instruments, just whispers of ancient violence translated into the quiet hum of scientific analysis. We can study them without fear, contemplate them without alarm, marvel at their power while remaining safe in our small corner of the cosmos. And perhaps there is something deeper here as well, something about the nature of energy and light that speaks to the fundamental structure of reality. The electromagnetic spectrum from radio waves to gamma rays is a single phenomenon, a unified expression of the interplay between electric and magnetic fields propagating through space. The differences between a gentle radio wave and a searing gamma ray are differences of degree, not of kind. They are both light, they are both electromagnetic radiation, they are both manifestations of the same underlying physics, the same fundamental laws that govern the universe at every scale. This unity is beautiful in its way. It suggests that the cosmos, for all its variety and complexity, is built on simple foundations. The same equations that describe the radio waves from your Wi-Fi router describe the gamma rays from a distant cosmic explosion. The same principles that govern the light in your bedroom govern the light from galaxies billions of light years away. There is a coherence to reality, a consistency that allows us to understand distant phenomena using knowledge gained from local experiments. The universe plays fair in this sense. It follows the same rules everywhere, allowing us to extend our understanding from the familiar to the unimaginably remote. As you rest now, perhaps feeling the gentle pull of sleep, consider the light around you with new appreciation. The soft glow of your surroundings is just one octave of a vast cosmic symphony. Beyond your perception, radio waves are passing through you at this very moment, carrying signals from stations you will never hear, from satellites you will never see. Infrared radiation is streaming from your body, your warmth made manifest in invisible light. And far above you, beyond the atmosphere's protective embrace, gamma rays from distant galaxies are arriving at Earth, carrying information about events that occurred before our planet was born. You're immersed in light, surrounded by it, permeated by it. And this light connects you to the cosmos in ways both immediate and profound. The visible light from your lamp began as nuclear fusion in a distant power plant, converted to electricity, transmitted through wires, and transformed once again into the photons that now enter your eyes. But trace that energy back far enough, and you find that it originated in the sun, in the nuclear furnace that has powered life on Earth for billions of years. And the sun's energy came from the gravitational collapse of a cloud of gas that was itself forged in the hearts of earlier stars that lived and died long before our solar system formed. The light around you is recycled starlight, ancient energy transformed and transformed again until it illuminates your quiet evening. This is the deep truth of our connection to the cosmos. We are not separate from the universe we observe. We are part of it, made from its materials, powered by its energies, illuminated by its light. When we study gamma-ray bursts, when we analyze the most energetic light in the universe, we are the universe studying itself, contemplating its own extreme possibilities, wondering at its own capacity for violence and creation. And now, as we prepare to move deeper into our exploration, let us pause for a moment to appreciate where we are. We have introduced the mystery of gamma-ray bursts, those brief flashes of the most energetic light in the universe. We have traced the history of their discovery, from Cold War satellites to modern space observatories. We have explored the electromagnetic spectrum, understanding how gamma rays represent the extreme high-energy end of a unified phenomenon called light, and we have begun to wonder together about the mechanisms that could produce such extraordinary events. The night stretches before us, filled with more mysteries to explore, more questions to contemplate. We will journey into the hearts of dying stars, witness the collision of impossible objects, and trace the light across billions of years to understand why it carries such extraordinary energy. But there is no rush. The cosmos is patient, and so are we. Let the knowledge settle gently, like sediment drifting to the bottom of a still pond. Let the wonder fill you slowly, peacefully, like starlight filling the darkness between worlds. If you're still here, still traveling with me through this cosmic night, I am grateful for your companionship. Consider sharing in the comments what has captured your imagination so far. Is it the accidental discovery of gamma-ray bursts by military satellites? The vast range of the electromagnetic spectrum? The inconceivable energies involved in these cosmic events? Whatever has sparked your curiosity, I would love to hear about it. These journeys are always richer when shared, when we know that others are contemplating the same mysteries under the same stars. Now, let us continue our exploration, moving from the nature of light itself to the cosmic processes that give rise to gamma-ray bursts. For if we want to understand why these bursts produce such energetic light, we must first understand where they come from. We must journey to the places in the universe where such extreme energies are possible, to the death throes of massive stars and the violent mergers of exotic objects. It is a journey into violence and creation, into endings that are also beginnings, into the cosmic cycles that shape the universe we inhabit. The stars that fill the night sky, those gentle points of light that have inspired humanity since the first conscious eyes looked upward, are not eternal. They are born, they live, and they die, following life cycles that span millions or billions of years. And just as the manner of a star's life depends on its mass, so too does the manner of its death. Small stars like our sun will end their days gently, shedding their outer layers into space and leaving behind a dense core called a white dwarf, a quiet ember that will slowly cool over billions of years. But massive stars, those giants that outweigh our sun by 10 or 20 or even 50 times, face a very different fate. Consider a star 20 times the mass of our sun. Such a star lives fast and dies young, burning through its nuclear fuel in just a few million years compared to the billions of years a sun-like star can expect. The fusion reactions in its core proceed through successively heavier elements, from hydrogen to helium to carbon to oxygen to silicon, and finally to iron. Each stage produces energy that supports the star against its own gravity, maintaining the delicate balance that defines stellar existence. But when iron accumulates in the core, the process reaches a dead end. Iron fusion does not produce energy, it consumes it. The core can no longer support itself. In a catastrophic moment, gravity wins its long battle, and the core collapses. In less than a second, the core of a massive star collapses from a size comparable to the Earth to a size of just a few dozen kilometers. The density becomes so extreme that protons and electrons are crushed together to form neutrons, and what remains is a neutron star, a city-sized object with a mass greater than the Sun, spinning rapidly and possessing a magnetic field trillions of times stronger than Earth's. The collapse of the core sends a shockwave outward through the star, blowing the outer layers into space in a spectacular explosion known as a supernova. For a few weeks, a supernova can outshine an entire galaxy. Visible across intergalactic distances, a beacon marking the death of a star and the birth of something new. The elements forged in the star's core and in the supernova explosion itself are scattered into space, enriching the interstellar medium with the heavy atoms that will eventually form planets, and, ultimately, life. But for the most massive stars, for those that outweigh our Sun by 25 or 30 times or more, the story does not end with a neutron star. The core is too massive even for neutron degeneracy pressure to support it. Gravity continues its relentless compression, and the core collapses further, beyond any known state of matter, into a singularity hidden behind an event horizon. A black hole is born. And here is where gamma-ray bursts enter the picture. When a massive star collapses to form a black hole, the process does not happen cleanly or quietly. Matter from the star's interior continues to fall toward the newly formed black hole, swirling around it in a disk of superheated material called an accretion disk. This disk is a maelstrom of extreme physics, with temperatures reaching billions of degrees and magnetic fields twisted into impossible configurations. Along the axis of the accretion disk, perpendicular to its plane, powerful jets can form. These jets are composed of matter and energy accelerated to velocities approaching the speed of light. They punch through the outer layers of the dying star and burst into space, carrying with them the intense energy of the black hole's feeding frenzy. And as these jets interact with the surrounding material, as they collide with the gases expelled by the supernova explosion and with each other, they produce gamma rays of extraordinary intensity. This is the collapsar model, one of the leading explanations for the origin of long-duration gamma ray bursts, those bursts that last more than about 2 seconds. When we detect a long gamma ray burst, we may be witnessing the death of a massive star and the birth of a black hole, seen from across billions of light years, compressed into a brief flash of the most energetic light in the universe. But there is another type of gamma ray burst, one with a different origin and a different character. Short-duration gamma ray bursts lasting less than 2 seconds are thought to arise from a completely different process, the merger of compact objects. Imagine 2 neutron stars, the dense remnants of supernovae past, orbiting each other in a gradually tightening spiral. Such systems exist in our galaxy and throughout the universe, created when 2 massive stars in a binary system both end their lives as supernovae but remain gravitationally bound. Over millions or billions of years, these neutron stars lose energy through the emission of gravitational waves, ripples in the fabric of space-time predicted by Einstein's general relativity. As they lose energy, they spiral closer together, their orbital period growing shorter and shorter. Eventually, inevitably, they collide. The merger is cataclysmic. In the final moments, the neutron stars tear each other apart, their matter mixing and heating to extreme temperatures. If the combined mass is sufficient, the merger remnant collapses into a black hole, surrounded by a swirling disk of debris, and once again, jets form. Once again, matter is accelerated to near-light speeds. Once again, gamma rays are produced in quantities that briefly outshine the cosmos. But this time, the event is shorter, the burst more compact, the gamma rays slightly different in character. The merger is over in milliseconds, and so is the main burst of gamma ray emission. This picture, the collapsar model for long bursts and the compact object merger model for short bursts, represents our current understanding of where gamma ray bursts come from. But understanding the source is only part of the story. We still need to understand the mechanism, the precise physical process by which these extreme events produce light of such extraordinary energy. And this understanding, it turns out, involves some of the strangest and most fascinating physics in our universe. Picture the jet emerging from a collapsar or a neutron star merger. This jet is not like anything in everyday experience. It is moving at more than 99% of the speed of light. At such velocities, the normal rules of physics give way to the strange realm of special relativity. Time slows down, lengths contract, mass increases, and light itself behaves in peculiar ways. One of the key phenomena is something called relativistic beaming. When a source of light is moving toward you at a significant fraction of the speed of light, the light it emits gets concentrated into a narrow beam pointed in the direction of motion. Furthermore, the light gets blue-shifted, pushed to higher frequencies and higher energies. For a jet moving at 99% of the speed of light, this effect is dramatic. Light that might have been emitted across a wide range of frequencies gets compressed and amplified, transformed into the high-energy gamma rays we detect from billions of light years away. But relativistic beaming alone does not explain everything. Within the jet, there are multiple processes producing gamma rays. Shockwaves form as different parts of the jet move at slightly different speeds, colliding and creating regions of extreme heating and particle acceleration. Magnetic fields, twisted and amplified by the dynamics of the accretion disk, thread through the jet, accelerating charged particles to enormous energies. These particles, mostly electrons and positrons, then radiate gamma rays through processes like synchrotron radiation, in which charged particles spiraling in magnetic fields emit electromagnetic radiation. The details of these processes are still being worked out by scientists around the world. New observations from satellites like the Fermi Gamma Ray Space Telescope continue to refine our understanding, revealing complexities and subtleties that earlier models had not anticipated. But the basic picture is clear. Gamma ray bursts are powered by the most extreme events the universe can produce: black hole formation and compact object mergers, and the energy is converted into gamma rays through relativistic jets and the exotic physics that governs matter moving at nearly the speed of light. Perhaps you're feeling the weight of all this information settling upon you, mixing with the gentle pull of sleep. That is perfectly fine. These concepts are dense and complex, but they are also beautiful, revealing a universe of extraordinary violence and extraordinary creativity. The same processes that create black holes also forge the heavy elements that make up our planet and our bodies. The same jets that produce gamma rays also distribute energy and material across intergalactic space. Death and creation are intertwined, ending and beginning merged into single cosmic events. And through it all, light carries the message. Light that began its journey in the chaotic aftermath of stellar collapse or neutron star merger travels for billions of years, crossing the expanding universe, passing through voids and past galaxies, until finally it reaches our instruments and our wondering minds. The gamma rays we detect today left their source when the universe was young, when our own solar system had not yet formed, when the Earth was not even a possibility. They are messengers from the past, from events so distant in time that they seem almost like dreams. There is a kind of magic in this, a kind of miracle that no amount of scientific understanding can diminish. We can explain the mechanisms, trace the physics, calculate the energies, but the sheer fact that we can do so, that the universe is comprehensible, that light carries information across billions of light years and billions of years to meet our patient investigation, this remains a source of wonder. We are small, yes. We are brief, yes. But we are capable of understanding, capable of wonder, capable of reaching out with our minds to touch events that occurred before our planet existed. And so we rest now, having travelled far into the heart of our cosmic mystery. We have explored the births and deaths of stars, the formation of black holes, the collision of neutron stars, the creation of relativistic jets, and the physics of gamma ray production. The picture is coming into focus, though many details remain to be filled in. We are beginning to understand why gamma ray bursts produce such energetic light, why they represent the extreme high end of the electromagnetic spectrum. But our journey is not complete. There is still more to explore, more questions to contemplate, more wonder to discover. The instruments that detect gamma ray bursts, the observations that have refined our understanding, the implications for our place in the cosmos, all of these await us as the night continues. For now, let the knowledge rest in your mind like a seed planted in fertile soil. Dreams may tend it while you sleep, watering it with subconscious contemplation. When you wake, the wonder will still be there, ready to bloom into deeper understanding. The cosmos continues its slow dance around you. Galaxies spin, stars burn, gamma ray bursts flash in distant darkness, their messages travelling toward us at the speed of light, and you, a brief flickering of consciousness in an ancient universe, have the remarkable ability to understand, to wonder, to dream. Whatever mysteries remain, whatever questions still hang unanswered in the cosmic night, we will face them together, you and I, one gentle step at a time. Light, as we've come to understand, is the universe's most faithful messenger. It carries information across impossible distances, preserving stories of ancient events in the energy and frequency of its photons. And nowhere is this message more dramatic, more extreme, more awe-inspiring than in the gamma-ray bursts that flicker from the depths of space. These brief flashes represent light at its most energetic, produced by the most violent events in the cosmos, and yet they reach us as gentle whispers, detected by patient instruments, analysed by curious minds, contemplated by travellers like us on quiet nights. The journey to detect and study gamma-ray bursts has been a remarkable one, spanning decades of technological development and scientific ingenuity. From the Vela satellites that first stumbled upon the phenomenon to the sophisticated observatories that now orbit our planet, each generation of instruments has peeled back another layer of the mystery, revealing new details, raising new questions, deepening our appreciation for the extreme physics at play. Consider the challenge facing scientists who wanted to study gamma-ray bursts. These events are unpredictable, appearing without warning at random locations in the sky. They are brief, lasting from milliseconds to at most a few minutes, and their light cannot penetrate Earth's atmosphere, meaning that ground-based telescopes are useless for direct observation. Everything we know about gamma-ray bursts has come from space-based instruments, satellites designed specifically to catch these fleeting messengers from the cosmic deep. The Compton Gamma Ray Observatory, launched in 1991, was one of the great pioneers of gamma-ray astronomy. Named after Arthur Holly Compton, a physicist who made fundamental contributions to our understanding of gamma rays, this satellite carried 4 instruments designed to observe different aspects of the gamma ray sky. Its burst and transient source experiment was particularly important for gamma ray burst research, detecting and cataloguing thousands of bursts over the satellite's 9-year mission. The data from Compton confirmed that gamma ray bursts were distributed uniformly across the sky, ruling out local sources and pointing toward cosmological origins. But Compton could not pinpoint bursts precisely enough to allow follow-up observations at other wavelengths. This limitation meant that scientists knew gamma ray bursts were occurring, knew they were distant, knew they were energetic, but still could not identify their host galaxies or study the afterglows that might reveal more about the burst environment. The mystery remained tantalizingly incomplete. The breakthrough came with Beppo-Sachs, an Italian-Dutch satellite that began operations in 1996. Beppo-Sachs had the ability to determine burst positions quickly and accurately enough that ground-based telescopes could point at the burst location, while the afterglow was still visible. In February 1997, Beppo-Sachs detected a gamma-ray burst and relayed its position within hours. Ground-based telescopes quickly identified a fading optical source at the burst location, and within days, spectroscopic observations confirmed that the burst had occurred in a galaxy at cosmological distance. The debate was over. Gamma-ray bursts were truly coming from the distant universe. This discovery opened a new era in gamma-ray burst research. Suddenly, scientists could study not just the gamma rays themselves, but also the aftermath, the slowly fading glow that lingered for hours or days or weeks after the initial burst. These afterglows provided crucial information about the burst environment, the host galaxy, and the physical processes at work. They allowed astronomers to measure distances, to estimate energies, to test theoretical models against observation. New satellites followed, each more capable than the last. NASA's SWIFT satellite, launched in 2004, was designed specifically to catch gamma-ray bursts in the act and quickly alert ground-based observers. SWIFT carries 3 instruments: a burst alert telescope that detects and locates gamma-ray bursts, an X-ray telescope that observes the early afterglow, and an ultraviolet shot optical telescope that tracks the fading light at longer wavelengths. When SWIFT detects a burst, it can automatically slew to point its narrow-field instruments at the burst location within minutes, capturing data that would otherwise be lost. And then there is Fermi, launched in 2008 and still operating today. The Fermi Gamma-Ray Space Telescope is the most sensitive gamma-ray observatory ever built, capable of detecting gamma rays across an enormous range of energies. Its large-area telescope can observe the entire sky in gamma rays, while its gamma-ray burst monitor is specifically designed to catch and characterize bursts. Fermi has detected some of the most energetic gamma-ray bursts ever observed, including bursts that emitted individual photons with energies exceeding 100 billion electron volts, far higher than anything previously recorded. These instruments are technological marvels, each one a testament to human ingenuity and the desire to understand the cosmos. They orbit high above our atmosphere, their electronic eyes turn toward the sky, waiting patiently for the next flash of gamma-ray light. When a burst occurs, they spring into action, recording data, calculating positions, alerting observers around the world. In minutes or hours, telescopes on multiple continents may be pointing at the same patch of sky, observing the same fading glow, contributing data to the same scientific puzzle. If you're still with me on this journey, still drifting through the cosmic night, I wonder what you find most remarkable about this enterprise. Is it the technology that makes such observations possible? The international cooperation that coordinates responses across continents and time zones? The patience required to wait for events that cannot be predicted? Whatever aspect captures your imagination, I would love to hear about it. Consider leaving a comment below, sharing your thoughts with fellow travelers who are also making their way through this cosmic darkness. The data gathered by these satellites have transformed our understanding of gamma-ray bursts. We now know that there are at least 2 distinct categories: long bursts lasting more than about 2 seconds, typically associated with the collapse of massive stars, and short bursts lasting less than 2 seconds, typically associated with compact object mergers. We know that the bursts emit energy across the entire electromagnetic spectrum, not just in gamma rays, and that the afterglows can be observed for days or weeks as the ejected material interacts with its surroundings. We know that gamma-ray bursts are extraordinarily luminous, outshining everything else in the universe during their brief moments of glory. We know that they are accompanied by relativistic jets, outflows of matter moving at more than 99% of the speed of light. We know that these jets are responsible for the extreme focusing and amplification of the emitted light, transforming the energy of the explosion into the concentrated gamma-ray beam that we detect. And we are beginning to understand the detailed mechanisms by which the jets produce their gamma rays. Internal shocks within the jet, caused by variations in the outflow speed, create regions of intense particle acceleration and radiation. Magnetic reconnection, the sudden release of energy stored in twisted magnetic fields, may play an important role in some bursts. The interaction of the jet with the surrounding medium creates an external shock that powers the long-lived afterglow. Each burst is a natural laboratory for studying physics under conditions that can never be replicated on Earth. But perhaps the most remarkable discovery of recent years has nothing to do with gamma rays at all. In August 2017, the LIGO and Virgo gravitational wave detectors observed something extraordinary. The gravitational wave signature of two neutron stars spiraling together and merging. Just 1.7 seconds after the gravitational waves arrived, the Fermi satellite detected a short gamma-ray burst coming from the same location in the sky. For the first time, scientists had observed the same cosmic event in two completely different ways. Through gravitational waves, the ripples in space-time predicted by Einstein, and through electromagnetic radiation, the gamma rays that had been puzzling astronomers for decades. This detection, designated GW17B08.7 and GRB77 A, was a watershed moment for astronomy. It confirmed the long-suspected connection between short gamma-ray bursts and neutron star mergers. It inaugurated the era of multi-messenger astronomy, in which cosmic events are studied using multiple independent channels of information. And it provided unprecedented insight into the physics of compact object mergers, including the production of heavy elements like gold and platinum in the neutron-rich debris. Imagine the moment of detection. The excitement in the control rooms and observatories around the world. Gravitational waves from a neutron star merger arriving at Earth after traveling for 130 million years. Gamma rays from the same event arriving just 1.7 seconds later, delayed by the time it took for the relativistic jet to form and break free of the merger debris. Optical and infrared telescopes swinging toward the source, capturing the fading glow of a kilonova, the radioactive decay of the newly forged heavy elements. Radio telescopes detecting the emission from the jet as it expanded into the surrounding medium. For weeks, astronomers studied the event at every accessible wavelength, building up a comprehensive picture of one of the universe's most extreme phenomena. This is the cutting edge of gamma-ray burst research, the frontier where new discoveries are being made and old questions are being answered. We are no longer just detecting these events and wondering what they are. We are understanding them, tracing their origins, deciphering their messages, connecting them to broader cosmic processes. The fastest light in the universe is yielding its secrets to patient investigation. And yet, for all our progress, mysteries remain. Not all gamma-ray bursts fit neatly into the standard categories. Some show unusual properties that challenge existing models. The precise mechanism of jet launching is still debated. The role of magnetic fields in the energy extraction process is not fully understood. The physics of the prompt gamma-ray emission, the initial burst of high-energy light, remains an active area of research. This is the nature of science, thus of course. Each answer reveals new questions. Each discovery opens new avenues for exploration. The mystery is not solved so much as it is deepened, enriched, transformed into a more detailed and nuanced puzzle. And for those of us who find wonder in the unknown, this is good news. There will always be more to discover, more to contemplate, more to dream about on quiet nights. As you drift now, perhaps closer to sleep, perhaps hovering in that gentle threshold between waking and dreaming, consider the light that has travelled so far to reach us. Those gamma-ray photons, born in the violence of stellar collapse or neutron star merger, accelerated to unimaginable energies in relativistic jets, have been travelling for millions or billions of years. They have crossed the expanding universe, witnessed the formation of galaxies and the evolution of cosmic structure, passed through voids of unimaginable emptiness and regions of dense galactic clustering. And finally, At last, they have arrived here, at this moment, to meet the instruments we have built and the minds we have trained to understand them. There is something almost miraculous about this connection across cosmic time. The events we observe happened so long ago that they seem less like current news and more like ancient history. When the most distant gamma-ray bursts occurred, the universe was a fraction of its current age. Life on Earth had not yet emerged from the primordial seas. The sun had not yet formed from its nascent cloud of gas and dust. These bursts come from a time so remote that it challenges our ability to comprehend it, and yet here we are, receiving their messages, interpreting their meaning, marveling at their power. The instruments that make this possible will continue to improve. New satellites are being planned, more sensitive and more capable than anything that has come before. Ground-based gravitational wave detectors are being upgraded, and space-based detectors are on the drawing board. The era of multi-messenger astronomy is just beginning, promising new insights into gamma-ray bursts and the extreme physics that produces them. And somewhere out there, at this very moment, a gamma-ray burst is probably occurring. A massive star is collapsing, or two neutron stars are merging, and a jet of relativistic matter is punching through into space, generating a flash of gamma rays that will travel for billions of years before reaching any observer. The universe continues its endless cycle of creation and destruction, birth and death, ending and beginning. And we, small and brief as we are, have found ways to witness these cosmic dramas, to understand their mechanisms, to feel the wonder they inspire. The night deepens around you now, and sleep perhaps draws closer. Let the images of distant explosions and patient satellites drift through your mind like clouds across a starlit sky. There is no urgency here, no alarm, no threat. These events are far away and long ago, their violence transformed by distance and time into gentle data. Peaceful knowledge, quiet wonder. You're safe in your bed, beneath your familiar ceiling, surrounded by the ordinary comforts of your life, and yet through the magic of understanding, you're also connected to the most extreme events the universe can create, part of a vast web of information and meaning that spans billions of light years and billions of years. This is the gift of science, the gift of curiosity, the gift of the human mind's restless need to know. We cannot visit these distant explosions, we cannot feel their heat or hear their sound, but we can understand them, and in that understanding, we find a kind of intimacy with the cosmos that transcends mere distance. We are not strangers to the universe. We are its children, made from its materials, illuminated by its light, capable of comprehending its mysteries. And so we rest, having journeyed far into the realm of gamma-ray bursts, having explored their discovery, their sources, their mechanisms, and the instruments that reveal them to us. The night stretches on, filled with more mysteries to contemplate, more questions to ponder, more wonder to savor. But for now, let the knowledge settle gently in your mind. Let the images of distant galaxies and relativistic jets mix with the approaching dreams. The cosmos will still be there when you wake, still sending its messages of light, still waiting for you to wonder. If you're still here, still traveling with me through this cosmic night, I am grateful for your companionship. Consider sharing in the comments what has captured your imagination in this part of our journey. The satellites that watch for gamma-ray bursts, the historic detection of gravitational waves alongside electromagnetic radiation, the realization that we are witnessing events from billions of years ago, whatever has sparked your curiosity, I would love to hear about it. We are all fellow travelers here, making our way through the darkness together, finding light wherever we can. The story of gamma-ray bursts is far from over. There are implications to explore, connections to make, perspectives to gain. We have learned what these bursts are and where they come from and how we detect them, but we have not yet fully considered what they mean, what they tell us about our place in the universe, what philosophical and existential reflections they inspire. These contemplations await us as the night continues, as sleep draws closer, as the cosmos spins slowly around our small blue world. For now, let us pause and breathe. Let the weight of the journey so far settle into your body, into your bones, into the quiet spaces of your mind. You have travelled far tonight, from the familiar lights of your room to the relativistic jets of distant collapses, from the accidental discovery of Cold War satellites to the cutting-edge detections of modern observatories. You have earned this moment of rest, this pause before continuing deeper into the cosmic night. The gamma rays continue their eternal journey through space, carrying their messages of violence and creation. Satellites continue their patient vigil, waiting for the next flash of light. Scientists continue their work, analyzing data, building models, asking questions. And you continue your own journey through this night and through all the nights to come, a conscious being in an unconscious universe, finding meaning and wonder wherever you look. Sleep well, dear traveler. Dream of distant stars and ancient light. The cosmos holds you gently in its vast embrace, and the mysteries of gamma-ray bursts will wait patiently for your return. We have come far together, and there is still further to go, but the journey is not a race. Take your time, rest when you need to rest, wonder when you can. The universe is patient, and so are we, moving together through the endless night, following the light wherever it leads. The light that streams across the cosmos carries more than energy and information. It carries implications, consequences, meanings that ripple outward from the physical facts into the realm of philosophy and wonder. As we continue our journey deeper into the night, having explored the discovery, mechanisms, and detection of gamma-ray bursts, we now turn our attention to what these extraordinary phenomena mean for our understanding of the universe and our place within it. The gamma rays have traveled billions of years to reach us, and now we must ask ourselves what their message truly signifies. Consider for a moment the sheer improbability of our situation. Here we are, conscious beings on a small rocky planet orbiting an ordinary star in an unremarkable corner of a spiral galaxy, one among hundreds of billions of galaxies in the observable universe. And yet, from this humble vantage point, we have developed the technology and the understanding to detect and interpret signals from the most violent events the cosmos can produce. We have built satellites that orbit our planet, watching the sky for flashes of gamma-ray light. We have developed theories that explain how these flashes are produced, tracing the physics from collapsing stars and merging neutron stars through relativistic jets and shock-accelerated particles. We have connected these distant explosions to the very atoms in our bodies, recognizing that the heavy elements forged in such cataclysms are the same elements that make up our bones and blood, and the device you might be using to listen to these words. This connection between the cosmic and the personal is one of the most profound insights of modern astronomy. We are not separate from the universe we observe. We are part of it, intimately and inextricably. The calcium in your bones was forged in the heart of a dying star. The iron in your blood was created in a supernova explosion. The gold in any jewelry you might wear was likely produced in a neutron star merger, one of those very events that generates short gamma-ray bursts. When you look up at the night sky and contemplate the distant flashes of gamma-ray light, you are, in a very real sense, contemplating your own origins. This is not metaphor or poetry, though it is certainly poetic. It is literal scientific fact. The early universe, in the first few minutes after the Big Bang, produced only the lightest elements: hydrogen, helium, and trace amounts of lithium. Everything else, every heavier element on the periodic table, was created later, in the nuclear furnaces of stars and in the explosive deaths of those stars. The universe began simple and has grown complex over billions of years, building up the heavy elements that make chemistry possible, that make planets possible, that make life possible. Gamma-ray bursts are part of this cosmic story of element creation. The collapses that produce long gamma-ray bursts are also supernovae, explosions that scatter newly forged elements into space. The neutron star mergers that produce short gamma-ray bursts are particularly important for creating the heaviest elements, those beyond iron on the periodic table. When two neutron stars collide, the neutron-rich material ejected from the merger undergoes rapid nuclear reactions, building up heavy nuclei in a process called R-process nucleosynthesis. This process is responsible for creating many of the elements we consider precious and rare: gold, platinum, uranium, and dozens of others. The detection of gravitational waves and gamma rays from the neutron star merger G.17 provided direct evidence for this connection. In the days following the merger, astronomers observed the characteristic glow of radioactive decay from the newly created heavy elements. The light from this kilonova, as it is called, match predictions for what our process nucleosynthesis should produce. For the first time, we had direct observational confirmation that neutron star mergers create heavy elements, that the gold and platinum in our world were born in cosmic collisions of unimaginable violence. Think about what this means as you rest in your bed, perhaps wearing a ring or a necklace, perhaps with a smartphone containing tiny amounts of gold in its circuitry. That gold has a history stretching back billions of years, to a time when two neutron stars somewhere in our galaxy spiraled together and merged. The collision lasted only milliseconds, but in that brief moment, the conditions were right for creating elements that would eventually find their way into the gas cloud that formed our solar system, into the rocks of the early Earth, into the jewelry and technology of human civilization. You are connected to that ancient violence, not just philosophically, but materially. The atoms in your body and your possessions are cosmic artifacts, souvenirs from events as extreme as any gamma-ray burst. And perhaps there is comfort in this connection, a sense of belonging that transcends the apparent isolation of our small planet. We are not strangers to the universe, we are its children, made from its substance, participating in its ongoing story of creation and transformation. The gamma-ray bursts that flash in distant galaxies are not alien phenomena, utterly disconnected from our experience. They are part of the same cosmic processes that made us possible, the same cycles of stellar birth and death that have been shaping the universe since the first stars ignited billions of years ago. This perspective, sometimes called the cosmic perspective, has a way of transforming how we see ourselves and our world. The concerns that loom so large in our daily lives, the worries and anxieties that keep us awake at night, take on a different character when viewed against the backdrop of cosmic time and space. This is not to say that our concerns are unimportant. They are vitally important to us, to our loved ones, to the communities and societies we inhabit, but they exist within a larger context, a grander story that stretches from the Big Bang to the present moment and onward into an unimaginably distant future. Gamma-ray bursts remind us of this larger context. They remind us that the universe operates on scales of energy and time and distance that dwarf anything in human experience. A single gamma-ray burst releases more energy than our sun will produce in 10 billion years. The light from that burst travels for billions of years before reaching our detectors. The events that produce these bursts, stellar collapse and neutron star merger, involve densities and temperatures and magnetic fields that make anything on Earth seem gentle by comparison. And yet, these extreme phenomena are not chaotic or arbitrary. They follow the laws of physics, the same laws that govern the fall of an apple or the orbit of the moon. The universe is comprehensible, even in its most extreme manifestations. This comprehensibility is itself a source of wonder. There is no obvious reason why the universe should be understandable to beings like us. Our brains evolved to help us survive on the African savanna, to find food and avoid predators, to navigate social relationships and raise children. Nothing in our evolutionary history prepared us to understand relativistic jets or neutron star mergers or the electromagnetic spectrum. And yet, here we are, building theories and instruments that reveal the workings of the cosmos at every scale. The universe seems to welcome our inquiry, yielding its secrets to patient investigation, rewarding our curiosity with insights that transform our understanding. Perhaps you're feeling the gentle pull of sleep more strongly now, the weight of contemplation settling into a peaceful drowsiness. That is good. These reflections do not require alertness or effort. They are meant to drift through your mind like clouds, like the slow rotation of distant galaxies, like the patient travel of light across cosmic distances. Let them settle where they will. Let them mix with your dreams and your half-formed thoughts. The insights will still be there when you wake, ready to be examined in the light of day or savoured again in the quiet of another night. If you are still here, still travelling with me through this cosmic darkness, I am curious about what resonates with you. Does the connection between gamma-ray bursts and the elements in your body spark a sense of wonder? Does the cosmic perspective bring comfort or perhaps a touch of vertigo? Consider sharing your thoughts in the comments below. These journeys are always enriched by the reflections of fellow travellers, by the knowledge that others are contemplating the same mysteries under the same vast sky. The implications of gamma-ray bursts extend beyond the philosophical and into the practical, though practical may seem like a strange word to apply to events occurring billions of light years away. One question that scientists have explored is whether gamma-ray bursts could pose any threat to life on Earth. This is not a question asked from a place of fear, but from a place of scientific curiosity. If gamma-ray bursts are truly the most energetic events in the universe, what would happen if one occurred nearby? The answer, it turns out, is that a sufficiently close gamma-ray burst could indeed have significant effects on our planet. The gamma rays themselves would be absorbed by our atmosphere, but in the process they would trigger chemical reactions that could deplete the ozone layer, allowing harmful ultraviolet radiation from the sun to reach the surface. A gamma ray burst within a few thousand light-years of Earth, with its jet pointed directly at us, could potentially cause a mass extinction event by disrupting the atmospheric chemistry that protects life. But before any anxiety can take root, let us place this possibility in proper perspective. Such events are extraordinarily rare. Gamma-ray bursts occur somewhere in the observable universe perhaps once a day, but the observable universe is unimaginably vast, containing hundreds of billions of galaxies. The chance of a gamma-ray burst occurring close enough to Earth and with its jet pointed in our direction is vanishingly small. In the 4 billion-year history of life on Earth, it is possible that one or two such events may have occurred, perhaps contributing to ancient mass extinctions. But the probability of such an event happening in any given century, or any given millennium, or even any given million years is so low that it does not merit worry. Moreover, the distribution of the type of stars that produce gamma-ray bursts, the very massive stars that end their lives as collapses, is not uniform throughout the galaxy. These stars are more common in regions of active star formation, in the spiral arms of galaxies where gas and dust are dense. Our solar system currently resides in a relatively quiet region of the Milky Way, far from the intense star-forming regions where gamma-ray burst progenitors are most likely to be found. The cosmic geography of our location provides an additional layer of safety. So while gamma-ray bursts are indeed powerful, they're also far away, both in space and in probability. They are phenomena to wonder at, not to fear. They are reminders of the extreme conditions that exist in the universe. Conditions that are beautiful to contemplate from our safe vantage point. The violence of gamma-ray bursts is real, but it is also distant, transformed by space and time into data and theory and peaceful contemplation. And perhaps this is one of the gifts that gamma-ray bursts offer us, a sense of perspective that puts our own concerns in context. The universe contains violence beyond imagining, energies that dwarf anything in human experience, events that could sterilize planets and disrupt the chemistry of atmospheres. And yet, here we are, alive and conscious and curious, on a planet that has been nurturing life for billions of years. Whatever challenges we face, whatever difficulties mark our individual lives and our collective existence, we do so in a cosmos that has also produced stars and planets and the conditions for life and consciousness. The universe is not uniformly hostile. It is creative as well as destructive, nurturing as well as violent, and we are among its most remarkable creations. Let this thought settle into your mind as you rest. You are a product of cosmic processes, a descendant of exploding stars and merging neutron stars, a consciousness that has emerged from the long history of the universe and found itself capable of understanding that history. Whatever else may be true about your life, this much is certain. You are connected to something vast and ancient and ongoing. The gamma-ray bursts that flash in distant galaxies are part of your story, and you are part of theirs. The night continues to deepen, and our journey continues with it. We have explored the scientific facts of gamma-ray bursts, the mechanisms that produce them, the instruments that detect them. We have considered their implications for our understanding of element creation and our material connection to cosmic violence. Now let us turn to even deeper waters, to the philosophical and existential questions that these phenomena inspire. What does it mean that the universe contains such extreme events? What does it tell us about the nature of reality that gamma-ray bursts are possible? These questions take us beyond the realm of physics and into the realm of metaphysics, the study of the fundamental nature of being. They do not have definitive answers, at least not yet, but they are worth contemplating, worth holding in the mind like smooth stones, turning them over and examining them from different angles. One thing that gamma-ray bursts reveal is the extraordinary range of conditions that exist in the universe. Our everyday experience occupies a tiny sliver of this range. The temperatures we encounter span perhaps 100 degrees Celsius, from cold winter nights to hot summer days, from freezer to oven. But the universe contains temperatures ranging from nearly absolute zero, just a fraction of a degree above the coldest possible state, to trillions of degrees in the hearts of neutron star mergers and the jets of gamma-ray bursts. The densities we experience are similarly limited, air and water and rock, spanning a few orders of magnitude. But the universe contains densities ranging from the near-perfect vacuum of intergalactic space, less than 1 atom per cubic meter, to the inconceivable compression of neutron star cores, where a teaspoon of material would weigh billions of tons. Gamma-ray bursts sit at the extreme end of these ranges, in territories of temperature and density and energy that seem almost fictional, and yet they are real. They occur in the actual universe, governed by the same laws of physics that govern the world around us. The equations that describe the motion of a ball through the air also describe, with appropriate modifications, the motion of relativistic jets through space. The principles of electromagnetism that explain how a light bulb works also explain, in their more complex applications, how gamma rays are produced in shock-heated plasmas. The universe is unified by its physics, connected by the laws that operate at every scale. This unity is profound. It suggests that reality, for all its variety and complexity, is fundamentally coherent. The same rules apply everywhere, to the smallest particles and the largest structures, to the gentlest phenomena and the most violent. This is not something we could have predicted a priori. We might have lived in a universe where different regions followed different laws, where the physics of Earth bore no relation to the physics of distant galaxies, but we do not. We live in a universe that plays fair, that reveals its workings to careful investigation, that allows us to understand events occurring billions of light years away, using principles developed in laboratories on Earth. And perhaps this coherence points to something deeper, something about the nature of existence itself. Why should there be laws of physics at all? Why should the universe be orderly rather than chaotic? Why should it be comprehensible to beings like us, who evolved for entirely different purposes? These are questions that science alone cannot answer. They reach into philosophy and perhaps into spirituality, touching on the deepest mysteries of existence. Some find in these questions evidence of design, of purpose, of a universe that was created with intention. Others find in them nothing more than brute facts, features of reality that simply are without deeper explanation. Still, others find the questions themselves mysterious, marveling at our ability to even ask them, to wonder about the nature of wonder itself. There is no consensus here, no final answer that settles the matter, but the questions remain, hovering at the edge of our understanding, inviting contemplation. Gamma-ray bursts do not answer these questions, but they do sharpen them. They remind us how strange and extreme the universe can be, how far beyond our everyday experience its phenomena can reach. And they remind us of our own remarkable position as conscious beings who can contemplate these extremes, who can build theories and instruments to understand them, who can find meaning and wonder in the flash of distant light. As you drift now, perhaps closer to dreams, perhaps hovering in that liminal space where thoughts become images and images dissolve into sleep, consider the strangeness of your situation. You are a pattern of matter that has become aware of itself, a collection of atoms that has learned to ask questions about other atoms, a brief flickering of consciousness in a vast and ancient universe. You did not choose to exist, and you will not choose to stop existing when your time comes. But here, in this moment, you are alive and aware and wondering, connected by light and matter and physics to everything else that exists. The gamma-ray bursts that flash in distant galaxies are part of this everything. They are expressions of the same reality that produced you, governed by the same laws, made of the same fundamental ingredients. When you contemplate them, you are the universe contemplating itself, matter and energy arranged in such a way that it can ask questions about matter and energy. This is perhaps the strangest fact of all, stranger even than the extreme energies of gamma-ray bursts or the violent deaths of massive stars. The universe has produced beings who can understand it. We are the cosmos becoming conscious of itself. If you are still here, still traveling through this night of wonder and contemplation, I am grateful for your presence. This journey would be lonelier without fellow travelers, without the knowledge that others are also floating on these currents of thought, wondering about the same mysteries, marveling at the same strange and beautiful universe. Consider sharing in the comments what philosophical reflections have stirred in your mind. Does the connection between cosmic violence and human consciousness move you? Does the coherence of physical law inspire wonder or questions? Whatever thoughts arise, they are welcome here, part of the vast conversation that humanity has been having with itself and with the cosmos since the first conscious beings looked up at the stars. The night stretches on, and our journey continues. We have travelled far together, from the accidental discovery of gamma-ray bursts by Cold War satellites to the cutting-edge observations of modern space telescopes, from the physics of relativistic jets to the philosophy of cosmic consciousness. The gamma rays that have served as our guides continue their eternal journey through space, carrying their messages of violence and creation, indifferent to whether anyone receives them. But we are not indifferent. We are curious. We are wondering. We are alive in a universe that has produced us and that we are slowly learning to understand.